Look at a robot, we have the head, the middle, and the feet. We agree? So in a robot, when you have the head, the middle, and the feet, you need one like color for the head, one color for the middle, one color for the feet, and you made yourself a robot. We agree? Or we did it with clothes, where you had like a shirt, pair of pants, and socks, and you made an outfit. You needed one shirt, one pair of pants, one pair of socks, you got an outfit. And I told you that if you chose more than one of each, you can't use fundamental counting principle. We agree? And every single time you're using the fundamental counting principle, each of these lines contains one thing. It might contain a letter, it might contain a number, it might contain a shirt, it might contain a color, right? But it contains one thing. And when we use the word like Wonka, and I said it had to start with a W, well, you'd put a W here, and I could put one thing there, right? Because I only was one W in Wonka. But then I use that up and have to keep going, right? We're going to be talking about permutations and combinations. So today we're going to mainly talk about permutations, and permutations are when order matters. So when does order matter? When if you put it in a different order, you couldn't do the same thing. Okay? So like telephone numbers are permutations because order in which you put the number into your phone matters, correct? Or else someone could have the same numbers as you out of order in a totally different place and you get the same phone call, correct? Which is impossible. Same thing about like pins. I know I'm talking, but people are still understanding, so I'm not sure comprehending. Okay, so pins, to get into a bank account, does the order in which you put in your pin matter? Or can you get in with the same pin out of order? No, you can't, right? So order matters. License plates, order matters. If you're picking people for different prizes, order matters. Because the first, second, and third prize would be different. If you're picking people for the same prize, first, second, and third wouldn't matter, then it would be a combination. It wouldn't be a permutation. Okay? So we're going to look up here. You should be on lesson 2, which is this one. So we're down here. So a permutation is an arrangement of objects. If you ever get the word arrangement, or they say something is arranged, order matters. So when they tell you I'm going to arrange someone for a picture, that's a permutation. So if ever the word arrangement is used, that's a definite permutation question. So if we were arranging posters on a wall, which we did, we had 8 posters and we arranged 5 on a wall, it was a permutation. So if ever you see the word arrangement, it's a giveaway that it's a permutation. They don't have to always use that word, but when they do use that word, it's a permutation. Order matters. So arranging of objects in a definite order, order matters. So if I had 3 stuffies, a kitten, a puppy, and a bunny sitting here on my desk, and I want to just take them home in my backpack, I would pick up the kitten, the puppy, and the bunny, I'd pick them up, I'd throw them in my backpack, and I'd walk off. How many ways can that happen? I'll reenact it. Here are the 3 stuffies. I pick them up. I throw them in my backpack. And I put my backpack on my back and I walk away. How many ways can I do that? One way. I literally just took them, all 3 of them up, and I tossed them in my backpack and I walked away. Did the order matter in which I tossed them in my backpack? No. I was like a complete beast. I just picked all 3 up at once and tossed them in my backpack viciously and put them on my back. I didn't even put them in any specific order, and I didn't actually put them in my backpack lovingly. I just picked all 3 of them up and I tossed them in there, threw them on my back, and walked up. One way, correct? So that would be a combination because the order doesn't matter with those 3 objects. I just took them, I tossed them in. Even if I was all kind, and I took the kitten and I put it in, then the puppy and I put it in, then the bunny and I put it in, I'm still putting it on my backpack and I'm walking away with all 3 of them, correct? That's still only one way to do it, even depending on how many I put in, how I put in my backpack, still walking off with all 3. So there's one way. However, if I was like, man, I would really like to take a picture of my 3 stuffies, and you're like, that's never going to happen. My daughter does. She does. She uses that film that's really expensive that you put in those cameras, and then they're like those little tiny, yeah, and then you take a picture, and then it instantly gets you the picture, but the picture's like $1 each, and she takes pictures of her stuffies. So it's real. This is a real thing that could happen. You might be like, why would I? She does. Okay? So this can happen. How many ways could she, how many different pictures could she take? How much photo paper could she completely waste taking pictures of her kitty, her puppy, and her bunny. Well, let's pretend I put the kitten first. What could I put next to it then? Not another kitten. I have a kitten, a puppy, and a bunny. I could put a bunny, and then this would be a puppy. Or I could start with the kitten, then for a different arrangement, so she could waste more of my money taking pictures of stuffies. What could be here? A puppy or a bunny. And then now I've wasted all my kitten waste, so what could I start with? A bunny? But I could have a puppy or a kitten. Or I could start with a bunny and have a kitten or a puppy. Or I could start with a puppy and I could have a kitten or a bunny. Or a puppy and a bunny or a kitten. So she could literally waste 6 pictures if she wanted to make it so that every picture was different, right? Now, how could we show that? Well, we could show it with the fundamental counting principle, because we could say, okay, well, this is the first spot on the shelf, okay? And then we need a second spot on the shelf, and then we need a third spot on the shelf. We agree? So if I go to the very far left spot on the shelf before she takes a picture, how many options would I have here? How many for this first blank? Nope. How many different animals do I have for this first blank? I have 3. I have a kitten, a bunny, or a puppy. We agree? Now it doesn't say I can't repeat, so I must mean that I can. Is that true? No. It says I have a kitten, a puppy, and a bunny. If you're telling me you can repeat, then you're saying that there's more than one kitten. Is there more than one kitten? No, it says I have a kitten, a puppy, and a bunny. It's just like saying I have the word was. I have a W, I have an A, I have an S. I can't repeat, correct? So I have to box and hold one. So say I hold the puppy. Then what do I have left for this blank? The kitten or the bunny, which is 2. Pretend I hold the kitten. Then I would have the bunny. And what does this result in? 6, which is the exact answer of the previous, showing you all the ways that you could do it. Now, instead of typing 3 times 2 times 1 in your calculator, you could type 3 factorial. This is the exact same. When you can say blast off 3 times 2 times 1, blast off, then you can use the factorial symbol. So if you can rocket count, you can use factorial symbol. Let's remind you where it is. So you're going to press the 3, and you need a calculator that is not your phone. So you're going to press the 3, and then you're going to press math, and you're going to arrow to the left to probability, and number 4. And hit enter. And you should get an answer of 6, because it's the exact same. Now I'm going to show you something else. If you don't repeat, and you start at a number like 3 and you go down by 1, you can also use the P for permutations. I'll show you what I mean. So here we have 3 times 2 times 1. So what we can say is I actually have 3 objects, the kitten, the puppy, and the bunny, right? And it's permutation because I'm arranging it. And if I'm putting down blanks like this, sorry to tell you, but you're arranging it. You're putting something on the left, you're putting something in the middle, and you're putting something on the right. You see that? You're physically arranging it. So I have 3, the puppy, the kitten, and the bunny, and I'm picking how many? 3 to arrange, correct? So put that into your calculator. Let me show you how you do it. So you go 3, and you're going to press math, and you're going to go to probability, just like you did before, and you're going to pick number 2, the NPR one. And then you pick a 3 again and hit enter. And you should get 6. Let's try it with a different scenario because it's a little less obvious here. So let's go back to that same one where we had 8 posters. And how many did we choose? Do you remember? Put on the wall? Yeah. We chose 5. So we had 8 and we chose 5. Now how we did that was I told you let's go right to the wall and let's pick our spots. So we have the left spot and the next spot and the next spot and the next spot and the next spot. So this is my wall. We agree? Now, how many posters did I have for the far left? Because it didn't say, like, I had to put my favorite poster in the middle. If I had to put my favorite poster in the middle, it would be 1 right there, correct? It did say that, but we're not doing that for this one. We're just putting 5 posters on the wall, right? So how many posters do I have? If that's the only restriction is that I have to put 5 of them up, not all 8. How many options do I have for this first blank? 8. Then I don't actually have 8 again. That's where the error comes in. People tell me I have 8, 8, 8, 8. Do you have an endless amount of the one poster? Because if you're going 8, 8, 8, 8, 8, you have an endless limited, like you don't have an unlimited amount of each poster. You could put up 5 of the same. And is that the case? No, you have 8 posters to put up. So if you have 8 posters to put up, you put 1 here. So how many do you have left? 7. Then you put 1 here. 6. Put 1 here. 5. Put 1 here. 4. And that's going to give you an answer. We agree? Now, if we go down by 1 in each blank, we can also use the P. So we have 8 posters. That's how many we have to choose from. And we're picking the P because order matters. Because if I rearrange these posters on a wall, I'm arranging them on a wall. If I arrange them on a wall, order matters because they would look different if I moved them around. We agree? So it's 8P. How many am I choosing though? 8P, 5. Type that in. Type this one into your main screen, type this one into your main screen, and hope we get the same answer, or I've taught you completely false information, which I have not, so you will. Type those 2 into your calculator. Mm-hmm. Yeah. So what are we getting? 6,720 for both of them. So you can go and get the answer for this, and this be your answer. We agree? And you're like, Lepp, I don't really give a crap about the P part, because I'm never using it. And then they say, hey, it's a numeric response. And it's in the form, I have 8 posters. I'm going to put 5 of them up on a wall. And your answer can be in the form A, P, B. Determine the values of A and B respectively. And you're like, oh, I only know the blank version, but there's nothing to notice in P. And then you're done. Right? You're done. So I have to make you know all the different ways, because then if they give you any different way, you can answer it for me. I'm not failing you. If I only teach you one way that you can do, then I might fail you if they ask it in a different way. Because then this would be 8 times 7 times 6 times 5 times 4. That's great. Your answer is 6,720. And their answer is a numeric response box where they're expecting 2 numbers filled in here and here. What are they expecting? They're expecting 8, P, 5. So they're expecting 8 and 5. And your answer is 6,720, which is lovely. It's right. It's just not at all how they're asking for it. Right? If they say respectively, they're asking for it in that order. So if they want the answer of A, B respectively, they want A, then B in the numeric response box. Okay? So that's what the respectively means. So they will only accept 85, they're not going to accept 50. And this number always has to be bigger or at least equal to this one, because you're picking from it. So I can't say, oh, I have 5 objects, I'm going to pick 8 and arrange them in a row. Does that make any sense? If someone walked up to you like, here's 5 objects, pick 8 of them, and then arrange them in a row, you'd be like, you have 5, and you're asking me to pick 8. Do you realize how dumb that sounds? But you'll still write it this way. So watch yourself, because that's what you're saying. You're saying, I have 5 items, I'm picking 8 to put in a row. And arrange them, which makes no sense. Can I say I have 8 and then picking 8? Yeah, guess what? That's the same as 8 factorial. Because it's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. It's 8 blanks, right? Can I say I have 8 and I'm picking none? Yeah, how many ways could you do that? Here's 8 objects, pick none. 1, I just stare at them. There's my one way. I'm picking none. They'd be like, can you physically pick none? And pick. I just did it. One way. So that's why 8p0 is actually 1, because there's one way. You just stare at the table and go, I want to pick some, but I'm not allowed. It's one way. Okay? We're going to flip over. So, factorial notation, I told you it's rocket counting. You start at the number and go down by 1 until you get to 1. So if, say it's like 8 factorial, that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 blast off. We agree? Now, 8 factorial, let's do something smaller. Let's say 5 factorial. 5 factorial is 5 times 4 times 3 times 2 times 1. We agree? But some people put 5 factorial in their calculator when they have this. 5 times 4 times 3 times 2. We are not blasting off, but they tell me that's 5 factorial. It's not actually 5 factorial, but it's the same answer as 5 factorial. Why? When you multiply by 1, what happens? Nothing. Absolutely nothing happens when you multiply by 1, right? So if I go 5 times 4 times 3 times 2, or I go 5 times 4 times 3 times 2 times 1, I'm still getting 5 factorial. Now, is this a true statement? Is this equal to this? Yes, only because it's equal to it because the 1 doesn't do anything, right? That's the only reason why. Okay, so here we have 6 factorial. It's 6 times 5 times 4 times 3 times 2 times 1, or in your calculator, it's 6 factorial, which is 720. But now we have 9 times 8 factorial. And what some people don't realize is 9 times 8 factorial is actually just 9 factorial. Now, why is that? Well, if I take 9 and I times it by 8 factorial spread out, let's see, I get 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 blast off, correct? Well, now I'm just going 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 blast off. So 9 times 8 actually gets itself to just be 9 factorial. We can write it just as one thing. Then we have 5 factorial divided by 3 factorial. Well, we can actually cancel these off, because if I take 5 factorial, and you see how I'm running equal signs down? So this is equal to this. I should have wrote this. Whenever it's an expression, it doesn't actually have an equal sign. So you run equal signs down the full left-hand side, because you're saying that this equals the next simplified version, correct? Because this 6 factorial equals 6 times 5 times 4 times 3 times 2 times 1, which actually equals 720. This is true statements. Like, if you look at it, it makes sense. 9 times 8 factorial equals 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, which equals 9 factorial. That's why we have equal signs in between them, because they are all equal. They're just different ways of representing the same thing. So if I have 5 factorial, 3 factorial, and I just don't put an equal sign, I just have random things floating on my page that are not equal, correct? But they really are. So the way you show that is you show expressions are equal by putting an equal sign running down the left. So I do 5 factorial over 3 factorial equals, well, how can I rewrite that? Well, 5 factorial is 5 factorial, or sorry, not 5 factorial. 5 times 4 times 3 times 2 times 1, and then 3 factorial is 3 times 2 times 1. And then what can cancel? The 3, the 2, and the 1. And what's 5 times 4? 20. Now, some people say, well, I can just put 5 factorial with 3 factorial into my calculator Lepp, and it just gives me the answer. True that. But what if I give you this? What if I give you 1020 factorial divided by 1018 factorial? Your calculator is going to say not today. It's too big. Okay? But you can still do this, because you know that 1020 factorial is just 1020 times 1 less, 1019 times 1 less, 1018. And then I can say, hey, it keeps going by putting the factorial symbol, can't I? And then on the bottom I have 1018 factorial, and then these cancel. And then my calculator can actually do that. It can do these smaller numbers, 1020 times 1019. which is 1,039,300. Okay, we're going to look here. What happens if I give you variables? So instead of telling you it's 7 factorial, I say it's n factorial. Remember, the factorial symbol just means I go down by one number each time, correct? So if I do n factorial, and I want to expand it, I go n, and then what's 1 less than n? Just n minus 1, that's it, right? I can't put it any better than that. 1 less than n is n minus 1. What's 1 less than n minus 1? N minus 2. What's 1 less than that? N minus 3. And then I'm going to put a factorial symbol because I could go on for life. Because if I don't know what n is, that could just keep going on forever, correct? Then I have n minus 1 factorial is n minus 1, and 1 less than that is n minus 2. 1 less than that is n minus 3, and now they're starting to match, so I'm just going to keep it. So here I have n minus 2 can cancel. The factorial is attached to the n minus 3, so those go together. And then the n minus 1 cancels. So all I'm left with is an equal sign running down the left. This equals n. This one, n plus 2 factorial, one more than that is n plus 1, or n plus 3, one more than that is n plus 4. So this is actually n plus 4 times n plus 3 times n plus 2 times n plus 1 times n minus 1. This is actually just n plus 4 factorial, expanded out of it. That's all that is. And then this, n plus 1 factorial over n plus 1. If I take 1 off of that, I get n plus 1, 1 less than n plus 1. If I take 1 off of that, I get n. 1 less than that is n minus 1. And then I can put a factorial symbol, meaning it just keeps going on for life. The bottom is n factorial. So I have n, and then I have n minus 1 factorial, and now they match. This matches this matches this, and I'm left with n plus 1. Your homework to finish for tomorrow are these 3.